Yeah, welcome to the last lecture in this series. This semester is also the last day of the semester today, and you have participated in a course that is called Introduction to Lattice Boltzmann, but we have also covered some more advanced stuff, and what this lecture should enable you, you get all the knowledge from it, is that now you should be able to actually develop new Lattice Boltzmann methods and introduce new concepts and things stuff, because you now understand how things work. Yeah, maybe not. I don't know. So this is a kind of a little bit what we tried to be able here to, and now we give ourselves a challenge. Don't know whether we put a challenge to us to develop a model. Yes, we do something relatively simple today. My dyslexia. So we derive a Lattice Boltzmann method for a simple diffusion equation. In 2D, so it's comparatively simple. We have a time derivative of a quantity C, which is a diffusion coefficient into the Laplace operator, so the second derivative on C. And with C being a concentration. And now two challenges. We want to have this model as simple as possible. And as a second challenge, as accurate as not as possible is not a good word, because as accurate as possible is, let's say as feasible. Okay, and we are going, as accurate as possible is not a good word, because then you ask a lot, yeah? So there's always what is the most accurate way of doing something. So we'll do this in a D2Q9 lattice. And we are applying the asymptotic analysis, and actually we are refining the asymptotic analysis for this a little bit. And this is all based on the expansion that we learned in lecture 6, of course, yeah? So, and I believe it's lecture 14 that we have, so it's equation 14.1. We get also from the from lecture 6. So this is repetition, yeah. So we have 0 is the sum over m, n, l, and q, being equal to 1 to infinity, with 1 m factorial, n factorial, l factorial, epsilon, our smallness parameter, by the power of 2m plus n plus l plus q, divided by m2, m plus n plus L, and this goes into the derivatives, the mth derivatives in t, the nth derivative in n, and the lth derivative in y, and I'm running out of space and coming into ma plus n b plus l to the order of q, 1 minus 1 by the power of n plus l plus m. I'm running out of space again, minus the collision operator to the order q, not aq, of a plus n, b plus l, half 1 now plus minus 1 n by the power of n l plus m. So this is what we derived in lecture 6, and I was just thinking, so if somebody hears this for the first time, they will stop, probably stop here. Yeah. So this is the asymptotic expansion that we got. I mean, is an addition of a Taylor expansion. Taylor expansion of the LBE and asymptotic expansion of the moment. Okay. And I guess you all know this by heart, right? Okay, so this is what we got if after taking the Taylor expansion and of this guy here. So the Lattice-Boltzmann equation, LBE, is Lattice-Boltzmann equation. Yeah, so the Lattice-Boltzmann equation in 2D is this post-collision state x minus ei, so the direction vector of the lattice times half grid spacing, t minus delta t half grid spacing minus the pre-collision part population x plus, so ij, so this is the direction times the vector times the grid spacing plus t plus delta t half, and this is equal to 0. So this is the symmetric form of the Lattice-Boltzmann equation. Yeah, it's symmetric because it is not evaluated at the lattice nodes and at the time step, but in between. Yeah, and you remember, so even though we apply the Lattice-Boltzmann method at the lattice nodes and at the time steps, the solution that we get is actually in between these. So, and this thing here is called the Lattice-Boltzmann equation, and this direction vector ij is of course the direction I and j. This is the same I and j as these indices, and we do this in diffusive scaling, so delta t is proportional to delta x square, and this gives us this epsilon square. This is diffusive scaling. So, and on top of this, we have a relaxation Ansatz, or relaxation time Ansatz. And for simplicity, now here we'll start with BGK. EGK, meaning that the moment MAB after collision is the moment before collision plus omega collision frequency MAB in equilibrium. So equilibrium is a design parameter. Yeah? So we can, when we design our method, what we can do, usually we have two choices. We can choose the omega and we can choose the equilibrium. This is what we design in order to get a specific method. Yeah? So minus MAB. And the this omega, which I sometimes call, maybe not completely accurate, the collision operator. So what I mean by this is this is what collision does. It is the state after collision minus the state before collision. Yeah. So this is what happens during collision. And I call it the collision operator, but the mathematicians would complain that this is not an operator. Yeah. Yeah, because it's not applied to something. So when I say this, I'm potentially saying this wrong. Let me see. I guess. Oh. Okay, I'll have to. Okay, now I think I was just thinking whether I wrote down this equation correctly. Yeah, if okay, we have to compare with what we had. Okay, let me see. When I have a mistake, I will potentially go back and correct it. So we have this MAB. MAB is MAB can now be restated as MAB over bar minus omega AB divided by 2. Yeah? And so this is the, so what is the meaning of this? So we define, okay, so our point is that we solve the Lattice-Boltzmann equation in between time steps and in between grid spacing. So now we define, instead of the pre-collision moment and the post-collision moment, we define an average between the pre and the post-collision moment, which we call this MAB over bar, where I have to warn you that in some literature these things are these things are twisted. So this, I'm usually consistent with this, but in other literature they call the pre-collision state over bar and the one in between without over bar. Yeah, sorry for that. So there's something some people did not agree, apparently. So now, if then this here is the state in between, then we get to the pre-collision state by subtracting half of this collision, and we get to the post-collision state by adding half of the collision. Okay, thank you for looking. We'll try to figure out in the next step whether this was with overbar or without overbar. Yeah, I hope I did not mess it up here. You see, now I made this bad joke. Do you know it by heart? Apparently, I'm not. Me not. I have to consult my my cheat sheet also. Okay, so now actually we want to get because we want to express everything in between where we evaluate our equation. We want to replace this here with the case where we have an overbar. So what we are going to do is we take this equation and plug in here this post-collision part, and then we plug in and the pre-collision part here, right? And then we come to m AB over bar plus omega AB half is equal to m AB over bar minus omega AB half plus omega m AB equilibrium minus MAB over bar, and now we have to add this plus, right, omega AB half. Okay, now what you obviously see, we get, first of all, we get rid of this guy here, yeah, the guy which we actually want to have. So the one place, so we want to solve this for MAB, but MAB here and here disappears. MAB over bar disappears, but we still have it here. And if we solve for this, we get MAB over bar is equal to MAB equilibrium minus 1 over omega minus 1/2 this capital omega AB. So this is what comes out when we solve this, and we call this here the tau, yeah, the tau that the original continuous BGK equation uses. So this is what we have in general, and now we want to build our model. We want to build our model, and now for building the model is we have to choose the conserved quantity, and you have to remember building a model is a creative act. So there is not a single way to build a model. You can do whatever you cannot do whatever you want, but there are many possibilities to do it in different ways. So, because we have to choose which moment we regard as our conserved quantity, and we also have to choose the asymptotic order of this thing, yeah? And I mean, we get often asked, so what is the right way to do it? Well, and you know, people get into fights over what you should do, yeah? But there is not a right way. So you decide something, and then you need to be consistent with yourself. Yeah, that's the right way. Yeah. So what we decide here is, of course, we decide something very simple and usual. We take the moment m00, yeah, and decide that this is our concentration. And now, so this is the moment that we had to decide, but we also have to decide on the order. Which order? So it, in general, makes sense to use an even order for a symmetric thing, and the even part that we choose is we choose 0, the 0 order. By the way, this is this is the most natural way in the sense that this is what everybody else would usually do. Yeah? Because this means that now your concentration does not depend on your resolution. And if you think about you write a finite difference, solver for the diffusion equation, you would not think about making your value field smaller with the grid resolution. Yeah? This is something that is useful in lattice Boltzmann if we are talking about the discretization of momentum, yeah, where we make this smaller because it is the variables that we put into the Navier-Stokes equation, u, yeah, the velocity. We make this smaller because we already have an error in the discretization of the velocity. Yeah? So this is our trick here. But now there is no reason for this trick. So we keep the order of this field independent of the resolution. Yes.
This one is equilibrium, right? We're defining this.
No, this is not equilibrium because this is, I mean, it's also equilibrium, but is a conserved quantity. So you say it will be the same in equilibrium and in non-equilibrium.
Okay.
So, okay. You see, I actually made this mistake. Let me briefly go back. Yeah. So this here, maybe you found this in lecture in your notes, lecture 6. Yeah.
I was checking out on the notes, but I couldn't find.
Yeah. So here, this was already the average part. This was is wrong. It's wrong in my notes here. This is why I miswrote it. Okay, writing things by hand will always lead to some mistakes. Yeah. It's always the duty of a good student to find out where the professor was wrong. Never trust equations. So, speaking of not trusting equations, now we trust that this is equation 41, can be restated in recursive form. And in this equation, we'll build in the BGK equation, which is kind of dangerous at this early stage, because if at a very early stage you already decide how you do your collision, you are not able to change it later. But for simplicity, we'll do it now into the equation. By replacing MAB that we have in the equation by MAB equilibrium minus tau omega AB. Yeah? So, and now, actually before I'm doing this, I want to point out some property of this equation. So, and this is about the leading term of the equation 14.1. Okay, well, because we did it wrong before, let's write it again. Let's see. Okay, now if we take the leading term in this thing is if we take the sum only from 0, 0 to 0, right? So this is what we are leading up. What is leading everything? So then it's epsilon by 2m plus n plus L plus Q. So you see, they are all 0, yeah? M2 plus M plus N plus L, so they are all 0. And here this derivative.
Shouldn't that be do this to 2m plus n?
No, 2m plus n down here. No, because this, okay, so this here, this up here comes from the asymptotic expansion, and in this in particular to the diffusive scaling. So in diffusive scaling, because m is the index that counts with the derivative of time, this is counted twice in the diffusive scaling in the asymptotic expansion. Down here, this is from the Taylor expansion. Yeah. So these things here and this here is part of the Taylor expansion, and therefore it's not included. So because this is the mth derivative. So and if m is 0, then this is no derivative, right? The same with xn dyl, and here comes a plus n. So again, n is 0, bl is 0. Here is the overbar. This is of order q. Here comes 1 minus 1 n plus l plus m. Now n plus l plus m is all 0, so this will become 1, so this will all disappear, right? So this will disappear. And then we have minus this omega a plus n, which is 0, b plus l, which is 0, to the order of q, this thing half, and now it's 1 plus minus 1 by the power of m plus l plus n, yeah, which are all 0, so this will become 0, so this will become 1, so this will become 2, so this will become 1 again, and there's no derivative, and all of these guys in front also become 1, which means that this thing here is omega ab q epsilon by the power of q. Yeah, so this is the leading part with a minus in front. So this, so in the beginning, in the leading part, we always have this omega AB. And now we are using this to build a strange, a strange looking recursive equation. Yeah, we say that omega AB by the power of k, not by the power, sorry, but to the order of k. So the entire equation is supposed, I mean, the sum to infinity, yeah, is supposed to become 0, right? So but the leading part of this is this guy here. So when I want actually to have an equation for omega AB to the order of k, what I can do is to put this to the other side, yeah, and add 0, and by adding 0, I'm adding the entire equation. And you see, there was this epsilon to the order of q. In this case, it's to the power of q. Yeah, so what I'm going to do, and I have a mistake in my writings here. Let's see. So I will multiply this by epsilon by the power of minus k. Yeah. And now now comes the sum m n l q equal to 0, and now with the condition that 2m plus n plus l plus q is equal to this k. And now comes the same term as before, m factorial n factorial l factorial, epsilon to the power of 2m plus n plus l plus q divided by 2m plus n plus l, and this goes into dt, the mth time derivative, the nth derivative in x, and the lth derivative in y, and you are happy that we do this only in 2 dimensions now. ma n plus n b plus l equilibrium at the order q minus tau omega a plus n b plus l at the order q. This time 1 minus 1 by the power of n plus l plus m minus omega a plus n b plus l, this to the order of q, half 1 plus minus 1 n plus l plus m. And now you can, if your little sister sees you doing this, you'll of course think you are crazy. Yeah. So we make it as, this is already as simple as I'm not 100% sure, but this is almost as simple as it gets. So what is the idea behind this? We have a separation of orders. Yeah. So this entire equation here on the right side gives you equations order by order. Yeah. But if we look only at a specific order, we have to extract only that specific order, and we get this specific order from this epsilon here. So what is summed up here is the order of that term. Yeah. So which means, because this is to the order 2m plus n plus l plus q, this altogether has to be k. Yeah. So we sum not to infinity, but we sum only for the case that all of this together is equal to k. That's what we are summing over. Yeah. So, and okay, a few sentences to this. Namely, what we are doing is equating coefficients. And this is because we have epsilon larger 0 is arbitrary. So the thing with equating coefficients is that this has to be true for any epsilon larger than 0, and this will only be true for any epsilon larger than 0 when it's true for all of the orders individually, right? This is the idea behind equating coefficients. So equating coefficients is something that in improving stuff for numerics is something that you always need to use, almost always. MAB equilibrium. So, and the other thing, of course, is that due to this asymptotic expansion that we made, yeah, so the important thing, and this is a must, and it is a mistake that's often done, these things, so the omega and the m equilibrium of k, these things do not depend on epsilon. That's very, very important. Yeah? I mean, the omega itself and the moment itself, they of course depend on they of course depend on epsilon, but only through the asymptotic expansion of them. Yeah? So the asymptotic expansion tells us how they depend on, because the asymptotic expansion is we take this moment and we have a serious expansion of epsilon with these different terms, and the different terms themselves never depend on epsilon. What did I want to say? Must not depend on, and we have to restrict of order epsilon by the power of k. So, I mean, this obviously means, let me get the red here, this obviously means that of course you can simplify the equation by compensating these two things. Yeah, so they will disappear. So we'll have no longer any epsilon in this. Okay, so then what is it doing in time? So now by this new thing we've gotten we have a strange equation here, yeah? Omega is equal to omega, but we know that the leading part of this will generate as an omega and will eliminate this guy, right? So this is why we have to place this here. And then obviously this omega, so there's an omega here again, which means this here is a recursive equation, yeah? We've generated a recursive equation where we have to plug the equation itself into itself again and again. Yeah? And there's, of course, then the question, will this converge? And fortunately, it will converge. Why will it converge? Any idea?
Because it is recursive?
No, recursion does not necessarily converge. So you're putting something into itself. So why would it ever end? Why would it end?
I'm thinking is that higher orders they do become zero, right? Or they have to become zero.
Okay, so we know. Well, not because higher orders become zero. No, that's not true. Actually, it's the opposite. At order 0 they become, in negative orders are 0. We only have positive orders. And see, so this.
Sorry, another question here.
Yeah.
So, if the tau is smaller, it has to go to 0, right? Or the idea is that if
No. We are not talking about the asymptotics of tau. Tau, for the purpose of this modeling approach, tau is a constant, and it does not matter whether this constant is large or small.
Okay.
Yeah. So because we have here a very stringent concept of smallness. Yeah. The thing that is small is epsilon, and everything else is not small. This is a mistake. This is a common mistake to assume, because then you have to expand tau. If tau is small, you have to expand it.
Okay.
Now here we assume that this is a constant. Yeah. The reason why this converges is because according to this sum, let's look here. We have the case that Q is equal to K if everything else is 0, and then all the derivatives is 0, and then this here will cancel with this, right? And in all other cases, MNL must be larger, one of them must be larger, so then this Q must be smaller than K. Yeah? So then when you have an omega K, it only depends on an omega Q where Q is smaller than K. Yeah? And since at omega 0, at omega to the power of 0, they all disappear, this will converge. Right? So it's since Q is equal, it can be the same, yeah, but then it will also disappear. This means that the recursion will converge. And this thing is a little bit unfortunate in as much as this recursive equation can become very ugly. So there's an interesting story which I potentially have already told, that if you know Stephen Wolfram is the guy who commercialized computer algebra with Mathematica. And there's also a dispute whether Stephen Wolfram invented the Lattice-Boltzmann method or not. Yeah, so most people think he did not, but he wrote an early paper and he believes or claims or whatever that he invented it. But this is not important. The important thing is that one of the first things computer algebra was used for was to get the equation that actually is solved with the Lattice-Boltzmann equation. Yeah. So this is computer algebra and Lattice-Boltzmann is somehow, is from the same family. Yeah. The problem is that if you have, one problem is that this kind of doing this is already very, very much simplified, because we do this for now 30 years. So this was when they did this the first time was in 1986. So it's almost 40 years. Yeah, 40 years basically. So. They made it much more complicated than we do it today. But still, it is still a pain, yeah, to be actually able to do this. So usually we have to do this with computer algebra even today. And computer algebra, of course, has become so much more efficient. Yes.
Is the paper of Wolfram the one of the cellular automata?
Yes. Yeah. So they basically, there was a dispute with Stephen Wolfram and Procel Haslacher. So Procel Haslacher is, he deceased in, I believe, around 2005 or so. So Stephen Wolfram basically said that Procel Haslacher stole this. I don't know. Science is not a nice. It's not always nice. So let's actually do this. It's not important who invented it. Let's just do it. Yeah. Okay. Applying 14.1 to the zero moment. So to the zero moment means we say that A is equal to 0 and B is equal to 0. And now we also have to choose our K, and let's start with K also being equal to 0. So if we do this, we get something pretty simple, omega 0, 0 at 0 order. You should already know that this is the case, but if not, just see. This is the one that we write in front, and because it's to the order 0, we have no derivative, so we'll just have 0, 0, 0, and then we see this guy is 0. Yeah? Okay, we see that in the beginning it disappears. So then we set k equal to 1, meaning that we have omega 0, 0 to the order 1 is again omega 0, 0 to the order 1, and we get out of our recursive equation, we get here that this is of order. So we get always the same thing back. So I guess I will start skipping over this yeah, soon, yeah, because they will always disappear. But then we also have the part that comes with the first derivative in x, and then we're counting this up, 1, 0, equilibrium, and now we have to count this down, yeah? Yeah, because for every derivative we count 1 epsilon up, so we have to count 1 epsilon down in this part here. So when here is a 1, then here must be a 0, minus tau omega 1, 0, and again this is of order 0, plus the y part m0, 1 to order 0 minus tau omega 0, 1 to order 0. Okay, now we know that these guys here will disappear, yeah, for the same reason that we had before, but what we actually have to do is we have to check this by using the recursion. So we take the same equation, yeah. Now we have to specify that, I mean, A is equal to 1 and B is equal to 0, and what is it, K is equal to 0, and then we come up that omega 1, 0 to the order 0 is omega 1, 0 at the order 0 minus omega 1, 0, and this is 0, and of course we'll observe the same thing also for omega 0, 1. This is also 0. So then we can determine that omega 0, 0 to first order is equal to dx m1, 0 equilibrium to 0 order plus dy m0, 1 equilibrium to 0 order. And this is not the equation that we want to solve, so we are not done here. Not yet. So, since we are not done, we just go up with k equal to 2, omega 0, 0 to second order is omega 0, 0 to second order minus omega 0, 0 to second order, plus dx, so we always have to count for every x derivative, we have to count 1 down, so we start with 1, so we'll end being now here at 1 minus tau omega 1, 0 to 1 dy m0, 1 equilibrium to first order minus tau omega 0, 1 to first order, and now also comes the time derivative. So the time derivative disappeared in the previous example because we said that all the moments and all the omegas for negative negative orders do not exist, yeah, and we have to always count down twice. So now we end up here with 0, 0 equilibrium to 0 order, yeah, minus tau omega 0, 0 to 0 order again, which we already know is 0. So now in this, what we still have to decide is this omega 1, 0 to first order. Yeah? So this, we have to apply the recursion here with a equal to 1, b equal to 0, and k equal to 1, which gives us an omega 1, 0 to first order is equal to omega 1, 0, why do I write this all the time? 1, 0 to first order plus dx. So, dx, so which moment comes? 0. 2, 0, equilibrium to which order?
Second order? No, this zeroth order.
zero order, minus tau, of course the same thing, so it's 2, 0, zero order, plus dy, which moment?
0, 2.
0, 2, 0 order.
It's 0, 2.
No, it's 1, 1.
1, 1.
Yes.
To zero order minus tau omega 1, 1, zero order. So we don't have any time. Yeah, we could write it, but it wouldn't be negative. Yeah, and of course we also have omega 0, 1. This is the other guy that we need. Okay, I'll skip over this boring part and say this is dx. Now it's obviously 1, 1, right? Equilibrium zero order minus tau omega 1, 1, zero order plus dy 0, 2, here it is, to zero order minus tau omega 0 to zero order. And of course now you've already understood that the things that come, these omegas to zero order, yeah, you can plug them all in. They always give you the same thing. Yeah, so to zero order they are all 0. So, and now this means we have convergence. Yeah, so, okay, we have termination. Let's say we have termination of the recursion. Because we have everything, we have eliminated all the omega, we only have tau left and we have the equilibrium left, and tau and the equilibrium is what we can decide on. So we'll call this now the equation 14.3 and say that omega 0, 0 to second order is now equal to dx. Now we plug everything in. M1, 0 equilibrium to first order minus tau dx M2, 0 equilibrium to zero order plus dy M1, 1 equilibrium to zero order plus dy M0, 1 equilibrium minus tau dx M1, 1 equilibrium to zero order plus dy M0, 2 equilibrium to zero order. I'm missing brackets, right? So plus dt M0, 0 equilibrium to zero order. So this is the equation that is being solved. And now we can decide on this stuff, and by so doing, we design our model. So we decide that M0, 0, which we have identified with our concentration, is the concentration and therefore deserved. So it's M0, 0 equilibrium is being M0, 0. And, okay, so this is conserved, is equal to C. And because it's conserved, the omega 0, 0, so the change in it, which is basically the source term, yeah, is, I mean, you can define a source term, but we didn't have any in our equation, so we said then it is 0, right? So, then in our equation, we did not observe any first, we did not see any first derivatives in space. But in our equation, we have first derivative in space, yeah? So they are these here. They are useful if you have a diffusion advection equation, yeah, so then you need these things. But now we only have a diffusion equation. So then these things here do not belong here, right? So that means what we decide to do is to say that this here, by the way, this is the stuff that we have under control, which means here are no orders, yeah? Yeah, so this is because we don't have the orders under control, yeah? So there's no order here, yeah? So these two things here, they are zero. So when they are zero, yeah, so we don't have any first derivative. We also, in our equation, we only have a Laplace operator, which means we don't have mixed second derivative. Is also not there. So what is this mixed second derivative? A mixed second derivative is x, y, yeah? So x, y on M11 and y x on M11, yeah? So if we don't have this, then we just say this guy here, M11 equilibrium, this is zero. Then it's, please.
Yeah, so why is there no first derivative in space? Do we get this from the original diffusion equation?
There is, so the equation that we are solving, yeah, I mean, I guess you already have it. So we want to solve this equation, and in this equation, there is no first derivative in space.
Okay.
Yeah. So then everything that gives us a first derivative of whatever does not belong here.
Okay.
And there is, of course, other equations like the Navier-Stokes equation that have first derivative in space, and then you would have to put something in this moment, right? So, no mixed derivatives. So this guy would be zero. And there are second derivatives. So we need some second derivative, or we need to have the second derivative to be correct. So I remind you, in the equation we have the Laplace operator C, which is dxx c plus dyy c, right? So this is the stuff that we want to have. And now you see we get dx on M20, and we get dy, okay, sorry. Yes, and there's a factor in front of it, right? Yes, but there's dy, also with tau, of course, on M02. Yeah. So this means that because they have the same tau in front of them, so they need to be the same. These two guys need to be the same, and they need to be proportional to C because we have the derivative of C. So what we are going to do is we propose that M02 equilibrium is M20 equilibrium is equal to M00, but we don't know, there could be a prefactor. And because I already know what it would be, I call this theta, which is the same that we usually use for this quantity. Okay? Which then will produce the following equation, if we plug this in, dt M00 to the zero order. So I put this on the other side. I take this guy to the other side. There's a minus in front of this all the time. So I'll have now dx. So we have tau dx. We have theta here, theta M00 to the zero order, plus dy theta dy theta M00 to the zero order, which can be written as the divergence of theta of tau times the gradient of theta m00 of 0 order. Yeah. So I mean there is something interesting here to remember. This is not exactly the same thing, the same way as you see it in your diffusion equation oftentimes. But the diffusion equation comes from physics, and physics actually does the same thing as Lattice-Boltzmann does. Or Lattice-Boltzmann, no, this was not fair. Lattice-Boltzmann does it the same way as physics does it, right? So there's an interesting thing is that this relaxation parameter is in between these two, yeah? And the other thing is in between these two derivatives, and this theta is in the innermost derivative. So if your tau or your theta, or if your diffusion coefficient, whatever, is not supposed to be constant, then this is something that you have to take care of. Yeah? And you see these two things would have different effects. If you change tau with space, or if you change theta with space, they would appear in a different position and will hence have a different reaction. Yeah? And then usually what we say in first semester physics, these things are constant and we plug them in front. But always remember, also in physics, this thing is here. So the relaxation rate, the mean free path is here, and the speed of sound is here. Yeah? So these things are not necessarily constant, and they have an effect if they are not. So let's say for simplicity, tau and theta constant, we get to our actual model, namely that is dt m0020 order would be theta tau, the Laplace operator on m0020 order. Yeah, and this is the equation that we want to have when we say that the diffusion coefficient is theta times tau, and this is equal to theta times 1 over our omega minus 1/2. Okay, so now we defined the moments that we had, but we also have moments that we have not talked about at all, namely the moments M1, M2, 1, M1, 2, and M2, 2. So what's about with them? Actually, funny thing is they have no effect. I mean, this is not completely true, but they have no effect at the order we were looking at the problem. Yeah? Always remember, the error comes at the next order, and the error can be large, and the error can be unstable, and whatever. Yeah? So this is only about consistency. For consistency, it does not matter what these moments are. And because it does not matter what they are, we now choose that M21 equilibrium is equal to M12 equilibrium, that this is 0 because they are unsymmetric. We would usually put them to 0. And for this M22 equilibrium, which is a non-symmetric, I will do something different. I would say that this is gamma times M00. So in principle, you could put this to 0 too, and it would not matter, but for consistency, but that could turn out to be a little bit problematic, or potentially very problematic, because this is even moment, right? Yeah, so I mean, all of these things, I mean, if you think about, because it's an even moment, and you add up the populations. If you say, so you're adding up populations. And in front of this, yeah, think about it, M00 is what? Is I square, J square, Fij. So all of them are plus, yeah? All of them are plus. This will be 1, 1 plus F minus 1, minus 1 plus F minus 1, 1 plus F 1 minus 1, yeah? So if you say that this here would be 0, yeah, there's a different thing here. Here you have J by the power of 1, so then half of them will be positive and half of them will be negative. If you say that this sum here is 0, then you specify something strange, yeah? So this is why I said better this is not 0, but something times the density, yeah? Okay, let's go to our lattice weights for the equilibrium moments, or lattice weights from equilibrium, say that. Yeah. From equilibrium moments. So I said we need to use computer algebra. I'm not showing it in detail. I'm just telling you what we do. So we have, of course, this definition of the moment. For computer algebra, it's always important that you also specify okay, so you have to tell computer algebra that in your world, 0 by the power of 0 is 1, yeah? Otherwise, the computer algebra doesn't do this by itself. Yeah, but you have to specify this, and then you solve. So you do this for all the moments that you have, and then you solve this for the populations. And after you did this, now let me specify that there is lambda and sigma is non-equal to 0, and lambda and sigma are the elements of -1 and 1. Okay, I think this is redundant, right? If they are only -1 and 1, they will not be 0. Okay, sorry. Okay, so for F lambda sigma, we can always write this as a quarter M11. So, okay, the lambda, and I just don't want to write all of them, right? So this lambda and sigma just give us a sign. It's either -1 or 1. And we have here lambda times sigma minus lambda M12 minus sigma M21 plus M22. Then we have the case that we have a population F, what did I do? Lambda 0 is 1/2 lambda M01 minus lambda minus, okay. I hope I'm not making any mistakes. So this is what the computer algebra brought out, at least I hope that I've written it down correctly. But if not, you should always, if you do it yourself, yeah, don't trust my notes, always do it yourself. Plus M02 minus M22. And then there is the F00 part, which is M00 minus M02 minus M20 plus M22. So now this is the way we compute the populations when we have the moments. And we get to the lattice weights. So the lattice weights, we'll find them as Wij, and if you look in papers written by Chinese people, you will often see it as omega ij, which I really hate, yeah, apparently because they don't see the difference between an omega, small omega, and a W, but this is a weight, yeah, and omega is an O, yeah, weight, so it's a W. Don't do this to me, never. Lattice weights are the populations at equilibrium and M00 equal to 1. So, I mean, for density 1, right? So we'll have, for example, M00 times M11 is 1/4 at the moments now at equilibrium, yeah, and we specified that this here is 0, so I'll write it again, equilibrium minus M21 equilibrium plus M22 equilibrium. Okay, so what did we have? We had this being 0, we had this being 0, and we have this here being gamma M11. Which means, yeah, so the case that we had previously, so if we say that gamma is equal to 0, yeah, what this implies, as we have seen above, that the weight for 1, is 0. And this is, of course, if I may go back, yeah, so this would be the weight for these populations, yeah? So they would disappear if gamma is seen to be equal to 0, yeah? So, and just to remind us what exactly this means, so we decided we start with this. Could I make it a little bit more beautiful? So this is the lattice that we started off with, right? And in this we have M. Okay, so the omega. So we do not distinguish between these guys, so they will all be the same, yeah. And this will be 1, 1, 1, 1. 1, 1, 1, 1, and we have, of course, also the 0 guy. So if this is D2Q9, this is and if W11 disappears, what we simply have, okay, we should try to draw it like this. Okay, let's say we have the 0 part 2. So what we do, if omega is, if W11 is 0, then we go to a smaller lattice, right? Yeah. So we have fewer populations, but as we saw from our equation, this M22 did not appear. So we could also decide it is 0, and then we have fewer populations, and then we do not need to solve. We basically just proved that we don't need this discretization. We can get along with this discretization and still being consistent. Okay, so let us see whether we can get this even more simple. And for this, let us look at M00 and W11 1, 0. So these are the guys that go in this direction. They would be 1/2 M1, 0 equilibrium minus M1, 0 equilibrium plus M2, 0 equilibrium minus M2, 2 equilibrium. And because these guys here are decided to be 0, what we end up with is 1/2 theta minus gamma M0, 0, which means that this W1, 0, which of course is the same as W0, 1, yeah, we said this is the same, is 1/2 theta minus gamma. So, and the last guy is M0, 0 omega, W0, 0 is M0, 0 minus M2, 0 equilibrium minus M2, 0 equilibrium plus M2, 2 equilibrium. And we observe that this becomes M0, 0, 1 minus 2 theta plus gamma. Okay, now there's another funny thing. There's minus theta in front of here, and basically what we could do, I mean, we could say that gamma is equal to 0, and now we could also say that theta is equal to 1/2, right? So then we'll have this guy equal to 0. And there is no reason from consistency point of view not to do this. So, which means we go here from the D2Q5, we can go to D2Q4, yeah, that's possible. And in this, we would simply have these guys here, minus 1, 0 equilibrium is equal to 0, 1 equilibrium minus 6 would simply be 1/4 C. Okay? So we can build our model like this, so plugging this equilibrium, and then we can say that we have an Fij after collision as being Fij plus omega Fij equilibrium, which is 1/4 C minus Fij before the collision, and we only have to specify that D is equal to theta. So theta, where theta is, as we identified, 1/2, yeah, 1 over omega minus 1/2. Okay, let's say this again. And then we have more or less the simplest possible model designed to solve this equation. And if you look at this model in more detail, you will find that this is, of course, not a new idea. It is the same as forward in time, central in space. Finite difference. So this is a very simple model, of course, that's well known and well understood. And what you discover is that this model here is basically just a different implementation, but it's 100% identical with forward in time, central in space finite difference solver. Yeah? Okay.
I have a question.
Yes.
Why would we choose theta is equal to half? Just to simplify the equation,
not yes. Because when we choose theta being equal 1/2,
Okay.
then W00 is 0. When in addition gamma is 0. Yeah? So to make it as simple as possible. So that was as simple as possible. Now as good. Do you think this is more difficult? As good as possible.
I have another question.
Yes.
So in the last one we said that gamma is going to be equal to 0.
No, you can't set it to 0. Yeah? Okay, we set it to 0.
Yes, but wasn't that not strange or
Yes, so okay, I said this would be strange. Okay, yes, I said it would be strange because it would set all of these to 0.
Yes.
Yeah, but then after you say, first you get a shock, well, then they will disappear. Then you ask yourself, well, then they disappear. So what?
Okay.
Yeah? I mean, this means you don't need to store them.
But wouldn't that mean if we, yes, they disappear, but setting gamma to 0 and having a D2Q4 model, somehow, imagining that the gamma is not 0, we would...
Yeah, so you end up with the D, so this setting gamma to 0 first forces you to actually to use a D2Q5, yeah? And in addition to this, you also put theta equal to 1/2, you have a D2Q4. Because you eliminated your degrees of freedom, they are no longer there.
But the D2Q5 would be more complete, right? Because we are not assuming that gamma is going to be 0, and we wouldn't get that strange...
So if we do not do this, we still have more moments.
Okay.
So now, because this the task was to do it as simple as possible, now we do it.
So for example, if we choose gamma and theta somewhere away from 0 and 1/2, then our model will be more complicated.
Yes.
But it would give the same results.
It would have the same consistency.
Same consistency. Okay.
Yeah, I mean, it will not give the same result. It will have a different error. So the result asymptotically will, yes, the asymptotic result will be the same. We have another, we still have a lot of, so there will be no exercise on top of the lecture today, but we still have a lot of lecture. So ask your question.
Yes, thank you. We want to use a lattice Boltzmann, or the thing is that the distribution function, or we have distributions to describe this equation, or we want to use a distribution. But
Yeah.
for doing that, we need to use the Hermite polynomials, or we have to discretize.
Yeah, we just discretized without Hermite.
But what we were doing is just, it was discretized, or we assumed that it's going to have this form, and then we looked for the way.
Yeah, you see, there is, who told you that you need to use Hermite polynomials?
Because in the lattice Boltzmann method, as we have the Maxwell Boltzmann distribution function, we can use.
So what? You can. You can.
Yes, we
In
can.
this case,
Yeah, you
where
don't
is
need
the
to.
system leading? Where is the system leading? Like in lattice Boltzmann, like the previous equations that we were solving, we knew that the equation was going to the distribution function, we are going to the equilibrium distribution function.
Yes, that's the same thing here, because we specified that we use BGK.
Okay, but then why aren't we evaluating the F equilibrium in this case?
Because in BGK we need, I mean, this is how BGK works.
My question is, how can we get this, for this equation, the discretization in space from 0, or not?
Okay.
That they are
Okay, I completely failed, because what we just did is coming from zero, doing the discretization and getting the model. This is what we did.
Yes, I know, but the thing, the step that I didn't see or that I'm just curious about is the distribution functions, because these distribution functions and the weights come from discretization.
So we have D2Q4, we have the weight for, so we have the equilibrium 1,4C, and you are done.
That's it.
That's it.
Yes, yes, I know, but what I'm trying to say is, how can I? First, we need to the idea is to discretize in space and time, and here we just discretize, or we took the discretization in space from.
So we have a lattice Boltzmann equation.
Yes.
Yeah. So that's what we already have, and now we specify the parameters of our. I mean, this is what. Now everybody talks about machine learning and artificial intelligence. You know what machine learning is. They have a model, they have parameters, and they fix the parameters. So what is the difference between us and them? They use data and we use analysis. Yeah?
Okay.
Yeah, so you can just use a lot of data observing diffusion and seeing what parameter fits your purpose. The other way is you know the equation that you want to solve, so you do analysis, and from this you determine the parameters. But both ways, data-driven and analysis-driven, is doing the same. You're finding you have a model space, yeah, like it could either be a neural network or it could be a lattice Boltzmann equation. They have parameters, lattice Boltzmann few. Neural networks many, yeah, but this is the same idea. You have these parameters, and you have to determine these parameters in order to solve the problem that you want to solve. All right. So, are you interested in the really funny stuff? Yes. Let's do it. The last lecture, so as good as possible. And for this, unfortunately, I mean, to do it in all its beauty and detail, we would need more time. So I'll do it a little bit. I don't go into all of the detail, yeah. But the thing that we are doing now is to use two relaxation times. Because we need to have more flexibility here, otherwise it would not work. So the assumption that we do so we have one relaxation time tau odd for odd and tau even for tau e for even moments. Okay, I'm not going to explain this idea in detail. It's also not the very best idea, but it's one that works for the purpose here. Yeah. So we have odd moments. Odd moments are the moments where you sum up the indices and they are an odd number, and the even moments are when you sum up the indices, they are an even number. Yeah. So meaning that 0, 2, 0, 0, 0, 2, 0, these are even moments, and M2, 2, this is an even moment. 1, 0, 1, 2, yeah, these are odd moments. And you just treat them differently with tau odd and tau even, okay? And your target equation, is still this, dt m00 to 0 order is equal to, we assume that all of this is constant. So the moment that we had to relax was the the moment in which we had the relaxation was the first moment, yeah? So the first moment is an odd moment, yeah? Therefore, this here comes out to be tau odd, yeah? Tau odd is the one that determines the diffusion coefficient, and tau even did not appear in our equation, so this is important, yeah? Tau even, only the odd part appeared in our equation, tau even did not appear in our equation, so it's a free parameter for us, again. So, say this again, no effect of tau even on the target equation. So, free parameter. So, now whatever we do to tau even, yeah, and to gamma and theta, we will have consistency. We'll not necessarily have stability, and when we have no stability, we'll potentially have no result at all, right? But we have consistency. So we have these things and can choose whatever we want. And the only way where this makes a difference is in the error. And therefore, we have to look at the leading error. So what is the difference with the leading error? Now this, as I said, requires computer algebra and can become pretty complicated, because what we have to do is we have to go to equation 14.2 and remind us, so we have to set up the equation for A is equal to 0, B is equal to 0, yeah, so the equation for the 0 moment. And then we had the equation for K is equal to 2. Now we remind us that we have in the symmetric, that this method is a symmetric method, so it's supposed to be second order accurate. In order to prove it, you would have to see what happens at K equal to 3. If you do it, you see everything disappears and is fine. So this error will disappear, but you will have an error at order 4. Yeah? And what we can do using asymptotic analysis is to get the equation for the error. Yeah? So, and in this, we have to make some inclusions and assumptions. So first we have to include the aliasing, that M, for example, that M30 turns out to be M10. So this is now specific to our discretization, of course. Yeah. We have to include conservation. Okay, this is trivial, of course. Conservation. And we also have to include all the equations that we have already derived at lower order. Or specifically at leading order. So basically the assumption is, so you have to assume, I mean you don't have to assume because you know from asymptotic analysis, but you have to reintroduce them, that your method solves the diffusion equation at leading order, yeah, because this is the precondition. So, and now, if you know you go and use computer algebra, you can put these things somehow here. So this I started this morning and I was not able to finish this, so I'm relying on my notes from the previous year. Yeah, but you see, this is kind of how it looks like. You would use some equation for making sure that you take care of the aliasing. Then you have, of course, the equation itself. Then you do a lot of reintroducing and recursions and a few other steps that we'll discuss. Yeah. So if you do this, usually requiring computer algebra, I mean, that's not true. You can do it by hand, but it's a very good exercise to do this by hand. So then we'll end up with 0 is equal to the 0 order of omega. So you do this omega 0, 0 to forced order, which is 0 because it's a conserved moment. Yeah? So then this turns out to have this equation. There's a time derivative of m0, 0. Okay, you don't need to write equilibrium for that because this is always an equilibrium. Yeah? And to second order minus tau odd theta, and you see this is already simplified. Yeah, so this is the equation that we solved there, m0, 0 equilibrium to second order. So this I will determine as part 1, yeah? And you see this is exactly the same equation that we originally wanted to solve, just 2 orders higher. But this does not come alone. We have other parts. And I hope that everything I write here is correct. If not, it's not actually the point. The point is more that it's possible to do this. Yeah, maybe if you really want to do it, you have to do it by hand later. Not by hand, but see it again yourself. So what we have is now. So these, by the way, these things here are to second order, so they are the errors. Yeah, there's not supposed to be anything of second order here. Yeah, but here we get a derivative of a 0 order, and this derivative of a 0 order is Laplace and time. So time derivative of the Laplace operator. Yeah, with some prefactors. So and this comes to a 0 order because this here is 2 orders, this here is 2 orders. Yeah. Plus tau odd theta divided by 6 minus tau even odd square theta, and here comes forced derivative in x, again of the solution, and forced derivative in y of the solution, plus, and we see this is gamma tau odd minus 6 gamma tau even tau odd square, and here comes dx dy m0, 0, 0 order. So okay, we have time once, space twice. Here we have space twice, and here we have space twice again. And now the important thing is that this here, what we call, I separate out this guy here as being part 2, and the rest I'll call part 3, yeah, and I call the entire thing 14.5. So now we have a problem because this m0, 0 to 0 order is the solution, yeah. So this is in general not 0. And if this is not 0 and it has a forced derivative, it will generate something that will change m0, 0 to second order. And m0, 0 to second order is the error. So this here is the equation for the error, the diffusion equation for the error. And this here is the source term to this diffusion equation. And the source term is not 0, and therefore the error will not be 0. Yeah? So let's specify these 3 parts. So one is the diffusion equation itself. for M00 to second order, this can be done zero. This can be 0 if the initial and boundary conditions are 0. I mean, if you have a diffusion equation, think about it, diffusion equation, you have 0 boundary conditions, you have 0 initial conditions, diffusion of 0, yeah, will disappear, so you're fine, right? Would not matter. And by the way, the boundary conditions to this will be 0 because you have the decision on the boundary conditions, yeah? And the boundary conditions that you specify are at order 0 and not at order 2, unless you specify them to be at order 2, right? So in order, if you want to have them at order 2, you would have to shrink them if you refine the grid. So if you keep them constant, the same value, while refining the grid, then it will be 0 order and the second order will be 0. So, you know, there will be no second order. So the equations, so the parts 2 and 3 together, these are the source terms. And they are the reason why why we actually have an error, because they depend on the solution, and the solution is of course not 0. The solution can be 0. M00, equilibrium or not, to 0 order, this is our solution. So, if our solution just so happens to have forced derivative, all their forced derivative being 0, then this will automatically disappear, and you would say, oh, nice, yeah, we get a forced order result. I mean, you can have conditions under which a bad method gives you correct high order results, right? Yeah, because you are lucky and things just disappear. But in general, this is not the case. And we are always interested in the general case. Now, the thing is, we would like to get rid of all of this. Yeah, so if this here is gone, then we have forced order accurate. Yeah, sorry, taking time. And we have parameters here, right? So we can choose these parameters. So tau odd is not a free parameter because it is a physical parameter, but tau e, theta, and gamma, they are all free parameters. Yeah, so problem that we have is we have three different parts here that we would get to 0. Okay, we also have 3 parameters. Yeah, okay, I get it. But there is one more simplification that we can do, and this is related to this guy here. And the thing is, we have here the time derivative of a spatial derivative of M00. And what we can do is we can exchange these derivatives. And the derivative, the time derivative of M00, this is something that we know. Yeah, because we know it from the diffusion equation. Yeah? So this is this is a step that we usually want to do. So we have the time derivative of M00 equilibrium. We can substitute this with the target equation. So then we have, so what will this give us? So in this we have a diffusion Okay, now let's write it down. That's the simplest thing. So dt Laplace m00 to 0 order. I don't write equilibrium because they're all equilibrium. So first thing is we do the exchange of the order of the operators. This is legal. Then we can write this as Laplace on the right-hand side of the diffusion equation. 0, 0 to 0 order. And this we put into 14.5. So now what you observe is there's a second derivative of a second derivative. Yeah. We assume that tau and theta, they are all constant. So when we do this and take now equation as 14.6, then we still have the same error equation here, up there. The same diffusion equation, I mean. So this I still call part 1. And then, you know, now I only have spatial derivatives, yeah? So I eliminated, so I already had the spatial derivatives, but I had the time derivative on top of this. By this means, I can get rid of all the time derivatives and only have spatial derivatives and group everything together in the 3 different ways we get spatial derivatives. So actually there will be only one, namely, this will simplify to tau odd theta divided by 6 minus tau even tau odd square theta plus tau odd square tau even theta. You see, this comes out of computer algebra. Tau odd to the 3rd power minus tau odd theta squared divided by 4. And all of this goes into dx to the 4th order m000 plus dy to the 4th order m00 to 0 order. And then we have the mixed derivatives. By the way, I'm going to call this guy here A. And have, in addition to this, gamma, tau odd minus 6 gamma, tau even tau odd square minus tau odd theta square half plus 2 tau even tau odd theta square plus 2 tau odd theta. Okay, I mean it looks ugly, so this is what the computer throws out. And this is the mixed second derivatives. And I'm going to call this guy here B. And then we recognize that this equation 14.6 gives a null solution, meaning it disappears, the solution to this disappears. So null solution means specifically this to 2nd order is always 0, right? If A is equal to 0 and B is equal to 0, because then this equation does not have any source term. So, which means that we can get a more accurate way of solving the same equation by specifying that this guy here, which I just write again, hopefully without mistake, you never know, odd squared. Okay, it's the exact values here is not important. This is the principle is important. Yeah. So being this equal to 0, so this is the first thing. This is A, and B is minus theta square plus 2 odd square plus 2 tau z theta square is equal to 0. And now, since we have used computer algebra so much, we have used computer algebra to ask the thing, now get us a result. Actually, we have a freedom here, yeah, because we have only 2 equations and we have 3 parameters. So, let's say we solve this for tau e and for gamma. So, hopefully, I know that I've given a similar lecture where these numbers were wrong. So I could not recover them today. So I just hope that these notes are now correct. Yeah. If not, and you want to do it, you have to do the algebra yourself, which is probably better because this is the exercise. So, but anyway, we can, if it was correct, then tau e is 2 minus 3 theta plus 12 tau odd square divided by 12 tau odd 1 minus theta. Now you see, one thing that does not work here very well is specifying that theta is equal to 1. That wouldn't work very well. And for gamma, we get theta divided by 3. Okay. So this is the result that we have, and now we can still choose theta. Tau odd we cannot choose, yeah, because there's a physical parameter. So now, if you remember what we talked about cumulants, and by extension, this also means for Hermite polynomials, yeah? So they react the same way. In there, the equilibrium value for the first moment is the square of the value for the second moment, right? So you would get theta. The gamma would be theta square. You may remember, yeah. So we had for the equilibrium for the second central moments we had 1/3, and for the first we had 1/9, yeah. So, which is interesting because you see for theta equal 1/3. Which we usually have, gamma would be 1/9, which we usually have. Yeah? So, then if you enter this, then you would have tau e is 1 plus 4 tau odd divided by 8 tau odd. Okay, so now this, if we did it correct, then this means that you have to plug in this tau even, this equation for tau even, to get a first order accurate result. Yeah? This is called a magic parameter, but actually this is not what is originally called the magic parameter, because from empirical observation, so people in the 90s, end of the 90s, people, De Humier and what's her name? De Humier and others. It's not fair to attribute this to De Humier. This was by Irina Ginzburg, sorry, yes. So they discovered that if you specify specific tau even, you get a much better result. Yeah, but they didn't analyze it in that way. they did it a little bit different, and therefore there was a little bit a different result. But let's try to recover this. So the thing is this tau odd. This tau odd is specifying the diffusion coefficient, and diffusion coefficient, your diffusion coefficient is often specified as being small. Yeah, you have small diffusion. So if this is small, so say it's much smaller than 1, yeah, then this equation there could be approximated by 1/8 tau odd. Yeah? I mean, by the way, this here is exact, yeah, but this is an approximation thereof for tau odd being small. And when tau odd is, so then you see that tau even would be proportional to something 1/tau odd. Yeah? And what has been described as the magic parameter in literature is lambda even odd being a constant when your lambda even odd is tau odd, tau even times tau odd. Yeah? And you see, if you put this to be a constant, then you can recover this particular behavior. Not exactly, because they didn't do the analysis to this degree of precision, but almost, right? So then you could say that this here would be 1/8. And so if you choose this magic parameter to be 1/8, then you get something that you could say is almost first order accurate. Okay.
Sorry, is that difference or a multiplication, the magic parameter? Theta even times theta odd, or theta
This is a
minus?
multiplication.
Okay.
Yeah. So the last famous last few words. So particular behavior of LBM is often seen for not necessarily this constant, yeah, could also be other constants for other cases, for other models. So lambda E odd, when this is constant, has been called the magic parameter. So this magic parameter, at least in this case, which is a very simple case, can eliminate the leading order error and therefore make the methods more accurate. I mean, substantially more accurate. So if it's approximated, is only, so you get also, you don't get necessarily first order if you do this, because this is only an approximation, but you get a much better result than if you do nothing. And you see that this implies to handle the collision in a different way from BGK, obviously. So first order convergence, or convergent. And the interesting thing with this is that this comes without any computational overhead. I mean, you just have two different rates, and you have to specify one rate in dependent on the other, and then you get a much better result. So this is also to some extent possible in the Navier-Stokes version. Yeah, that's a lot more complicated. Yeah, and actually it does not really work in 2D very well, but it works in 3D. and then you have to specify like 5 different relaxation rates in a very specific way, yeah, really strange, to get this higher order convergence, yeah. So, and yes, so this is something that you can in principle do with the stuff that we learned during this lecture series. So this was the last of this. I will now stop the recording. Thank you for attending all these lectures.